Hello, and welcome back to Science for Skeptics. I like to style myself as a friend to flat earthers, and that's what this video is all about. In this video, I'm going to apply some basic math and scientific principles to one of those skeptical ideas, the idea of relative density as a replacement for gravity. Before I get started, I want to get this out of the way. This is not a debunking video. I have specifically crafted this video to completely embrace the idea of relative density. We'll be looking into how things sink and float and how much force is behind that. And I'll be presenting a formula that works to predict these things based on their density. So what is relative density? So what is relative density? For one reason or another, some folks find the theory of gravity troubling. We all understand that if you drop a pen, it falls. But do we really need Newton or Einstein to explain that? What we can see from everyday observations tells us that things fall, except for the things that float. Ice floats in water and helium floats in air. A little observation and the pattern seems pretty clear. Dense things sink in lighter things. Could that be all there is to it? Maybe so. But can you give me a formula for this? Like maybe I'm designing a ship, or better yet, a submarine. Maybe I want to send a camera high up into the sky. How much helium am I going to need? How big does the balloon need to be? If I had some formulas for how relative density worked, maybe I could work these things out. Without further ado, here's the formula right here. I've never seen this formula anywhere on any flat earth video or posting. As far as I know, this is my own invention. Let's call this the law of relative density. All the formulas I've seen so far refer to the relative density as the ratio of the two densities. The insight here is that the relative density is governed by the difference of the two densities. Let me take you through this. I'm using the O subscript to denote an object and the M subscript to denote a medium. W sub O is the weight of the object. V sub O is the volume of the object. The Greek letter rho is traditionally used to denote density. So rho sub O is the density of the object, and rho sub M is the density of the medium. The difference right here is the term I'm calling the relative density. For this rock, we can calculate its weight by entering the density of the rock for rho sub O and the density of air for rho sub M. If we dunk the rock underwater, we keep the same rho sub O, but change rho sub M to the density of water. What this formula tells us is the rock is going to weigh less underwater, but how much less? There's one more parameter in this equation I haven't covered yet. The letter K is commonly used for a constant of proportionality. Those are fancy words, but the easy version is this is something we need to determine through experiment. The next step is to put this formula to the test. I don't expect you to just believe me. I expect you to design an experiment and see for yourself. Here's what I suggest. Collect some masses and measure their density. Choose some mediums and measure their density. Weigh out a quantity of the medium. Then hang your test mass in the medium so that it is neither touching the bottom nor the top, and weigh it again. Here I have a rock. It weighs 55 grams and has a volume of 21 milliliters. Here's some water. Together, the water and the cup weigh in at 980 grams. I hang the rock from a string and suspend it in the water. Now the cup weighs 1001 grams. That means the water is supporting 21 grams, leaving me 34 grams that I'm supporting with the string. Establish the density of your masses and your media, and then just plug those numbers into the formula and work out what K is for each one. If you measure carefully, I'm expecting to see you come up with a K very close to 1. K is just 1.0, but I'm planning to dig deeper into that term in the next video. I'm expecting there are some science nerds out there itching for a chance to tell us everything they already know about this equation. But I'll ask you to give everybody a chance first to try this out for themselves. If you do this experiment, please share your results down in the comments. But let's set all our textbook learning aside for a little while. For now, I want to dip our toes into a quick dimensional analysis. If you measure your weight in grams, as I have, and you measure your density in grams per milliliter and volume in milliliter, K appears to come out unitless. However, us science nerds are going to insist that weight should be a measure of force rather than mass. So that is why we need to keep the K in the formula. K is in units of grams force per gram mass. Hopefully all the science nerds are comfortable with that terminology. I mean, my scale doesn't read out in newtons. It reads out grams, right? So that's what I'm calling the law of relative density. I'd like to ask everyone to go out and check this formula and see how well does it match reality. This is a good place to start. It's a formula that tells us what floats and what sinks. It can tell us how much the rock should weigh underwater, and it can tell us how much the helium balloon can lift. Let's start with this, and next time we can explore the limitations of this formula, a formula which relates weight to relative density. See you next time.